All right, so let's go ahead and get started. Tobias, I've known you for quite a while. It goes way back to the very first Cloud Camp back in 2008. That was a lot of fun to watch you on your journey there from the very beginning of OpenShift. And if those of you don't know, Tobias is a co-founder of what later became OpenShift. At the time, it was a unknown company, named to be named later. And I think we forced you to come up with a name. I think it was OSS 1701 or something crazy like that.
Yes, it was the first name. Yeah.
And
source, enterprise open source software back then.
Yep.
Yeah.
That's right.
Yeah. The Trekkies would know the name. Yeah.
Yeah, that was pretty funny. Watch that happen. And then, of course, you guys turned it into Makara, and then it got acquired by Red Hat, and they turned it into OpenShift. And that's been quite a big success. You could make an argument that IBM acquired them primarily for OpenShift. So, yeah. That's wildly successful, I think, in the long run. But today you've got your startup Glasnostic, and we did actually have you speak here about 3 years ago, I think it was, roughly, when you were first launching. So a lot has happened since then, and I'm really excited to have you here speaking about basically what it is, what are the problems that you're seeing out there for large enterprises and service providers, and how can they solve those problems, especially around scaling and bandwidth and all that kind of stuff. So I'll let you introduce it better, but I did want to just take a moment to shout out, let folks know that you're a friend of Silicon Valley DevOps and of mine and of the communities, and we're really happy to have you. So with that, for those of you, again, who are online, we'll have a raffle at the end and give out some t-shirts and some stickers. So stick around. All right. Go ahead and take it away.
Yeah, thanks, Dave, for having me. It's always fun. We actually sat in, I think it was Cooper Cafe in Palo Alto, like in 2008 or something, and created the first version of this Cloud Camp.
That's right.
So yeah, it was like long time, and it was a lot of fun. So, anyways, but now a lot of time has passed, right? Obviously, totally different time. A little bit. Just to connect back to the OpenShift story, clearly spent a couple years at Red Hat, essentially telling anybody who wanted to know or not that PaaS is a stupid idea. That the PaaS to beat was really AWS at that point, because essentially PaaS is just a bunch of Lego blocks that you consume as a developer, and the best Lego blocks you could have, and still arguably one of the best Lego blocks, set of blocks you can have, is AWS in various forms, right? So back then, obviously, very much focused on how can we optimally support the building of applications, right? Make it as simple as possible. Take boilerplate out of that. And then what became pretty apparent then, and it leads exactly to this title of this talk here, is that nobody writes these applications anymore, right? As we started running OpenShift publicly at a large scale, it became clear that nobody there really had just a little Ruby or just a Java and talking to a database, right? Everything's connected. No application is an island anymore. So that really has tremendous deep ramifications for how you run this stuff, right? Also how you develop it, but mostly how you run it, right? So now talking about what is a rapidly evolving digital landscape? And of course, a picture is, is more worth more than 1,000 words. There are many names for that. My preferred term for that today is it's just a modern environment, but service landscape is fine. It's a little bit more technical. Accenture and calls it cloud complexity. More generic, but let's just call it a modern environment, right? So those are really large scale, highly composed and connected and very rapidly evolving sets of services, right? If you think in the first panel, like you start with a microservice application, that very quickly it evolves into something that is much more complex, that combines multiple applications. Now, you can't tell where the application there is anymore, right? But what you can tell is that, and it doesn't matter what these dots are, right? What you can tell is that it's a highly connected and likely very unstable and difficult to operate service landscape, right? Modern environment. And the point I want to make here, as clear as possible, and that's why it's an extra slide. We, in a past post-distributed systems world, what do I mean by that? It's too expensive to write distributed systems anymore, right? It's obviously, if you need a gazillion transactions in a sub-peta nanosecond, with full ACID compliance, then obviously you write a distributed system. That's a vanishing minority of systems that we do these days. It's way too slow, it's way too difficult, it's way too brittle, and it's way too expensive, right? So going back to this here, what really makes these systems that we have today in the enterprise different is that they are stitched together. We are wiring them up, we are composing them, if you prefer the better term, right? But it's essentially many teams deploying in parallel, stitching these things together. And those are not technically architected anymore, right? It's a confluence of services. Everything has an API, so by definition, I cannot know who's going to call me tomorrow, right? So that's the world we live in. That's what we call modern environments, and they're highly complex and highly dynamic. Now, what is also really important here is they fail differently than our applications used to fail, right? Failure in applications used to be very simply a defect in code, one or more defects in code. So you would debug it, you would test it, you would re-release it, and it would be fixed, right? Very much like in college when you wrote your computer science papers with LaTeX, right? It doesn't look like you wanted it to look. You go back into your write tech macros and then hope that it looks like it afterwards, right? You can't do this in these environments anymore, right? Your failures now look like this red graph. Bunch of things. It's large scale systemic, cascading a chain of events, highly nonlinear, right? Something may start here as a CPU issue, becomes a latency issue, then becomes a retry storm, and then just asymptomatic slowness or whatever it is, right? So, but each of these red dots starts throwing alerts. Right now, your engineering teams jump on the first alert they get, like it's your Facebook friend, right? It's totally counterproductive, right? The way we operate these things, because essentially these behaviors, these failure modes, are highly unpredictable, right? Now, there's a great talk, and I encourage everybody to go and watch this talk by Laura Nolan, back then at Google. Now I think she's at Slack. At the LISA 18 conference, that's the large installation systems administration, I think is the name, talk, where she talks about taxonomy of black swans. What are black swans, right? We remember thinking back when COVID struck, Robinhood went down for 3 days. There's a class action suit pending now. Turns out, oh, sorry, our DNS services got clobbered, right? They had nothing to do. There's nothing they could do about it, right? No classic back pressure they could do, right? So this talk identifies a couple typical cases, and number one among those causes why systems fail in large installations. And number one is you're hitting some stupid software limit somewhere that you didn't even know about, right? Something in a software component, oh, this load balancer craps out at like 2,000 connections, or oh, this database has a connection limit, or this hits you're running out of file descriptor somewhere, right? It's some random stuff, and then everything cascades from there. Slowness anywhere is crazy how much other slowness it begets, right? Cascading effects. So thundering hurts like we had at Robinhood, but that all these causes like affect anybody, right? The examples she talks about is that Spotify, it's Instapaper, it's Foursquare, Google, Reddit, like all the big ones are in there, right? Nobody's immune to these things, right? So highly recommend this. Just Google Laura Nolan's LISA 18 or Black Swans. Laura Nolan is Black Swans, right? Great talk. So what does that mean? It has direct consequences for observability. If you now think back, what do we do with observability today? Is we have a couple tools, right? We have metrics, we have tracing, we have logs, sometimes we have policies if we do a service mesh, right? But observability really only gets us that far. We can use observability for complex systems if they don't move very quickly, right? We can use observability to deal with systems that are fairly dynamic but not very complex. But of course, market forces conspire that everybody is getting pushed into the area that is complex and dynamic, right? But even that, observability is highly, highly manual work, right? You need to examine a lot of data. Anybody who has looked at something like this here knows that there isn't a time you can think of where this was insightful, right? Yet that's what we do in the observability space, right? It's more data. The idea of every product manager in an observability company is like, oh, more data, right? And it's always the data that's easy to collect, not the data that's meaningful, right? So observability has a natural limit what it can do, in particular with respect to how quickly an architecture evolves. Because if I have to look at these kind of data, I need to have a mental baseline. I need to have a model in my head. And Adrian Cockcroft has a great talk on that he keeps giving, and it gets better every time he does. You have to have a model in your head that is very static. So by definition, if you're scaling out, there's some dynamic, some elasticity in your architecture. New versions being deployed all the time. You're looking at something where you have 10 or 1,000 deployments a day. That doesn't help you at all. That helps you at a very local level, but nothing else, right? That helps you if you want to look at one red dot. But now remember, your failure mode is a whole network of red dots, right? So anyways, in that quadrant here, where we have to deal with complex and rapidly evolving service landscapes, digital landscapes, right? There's a lot of unpredictability in there that can be very disruptive. Now, these architectures are always running in a state of degradation. Typically, you don't even know it, you don't see it, it doesn't do much, but it can spiral out of control at a moment's notice. Very unpredictable, right? So in that regard, the environment is really what matters, right? You need super high level observability of how these systems behave, right? The deep observability here is a total distraction. It's a rabbit hole. That's the reason why it takes you a day to find out what you need to do. By that time, of course, the patient is dead, right? You're kind of like the doctor who says, well, we now know what happened. He had a stroke, an aspirin would have helped, but that was 8 hours ago. Now the patient is dead, right? Totally ridiculous if you think about it. So you need to step back, look at the forest, not the trees. The trees are not interesting, right? Not at all. We just think as engineers that they're interesting. In the large scheme of things, it's just one thing that anybody will just circuit break around, right? It's not important. Also, and I'm going to talk about this at the end of the talk, don't even think about root causes. There are no root causes anymore. At best, there's a confluence of factors that's very unlikely that it will come back in that constellation, right? Most importantly of all, you have no way of really doing anything in your lifetime. This is too much data. Right? You're never going to be able to analyze all data. So we come in there with super high-level observability, next-gen observability, and then real-time control, right? That you can apply anywhere and automatically. So that allows you to manage disruptions effectively. Now, before I dig deeper into that, I want to clear up one thing that's really, really important and most people don't think about, right? And that is that there are two axes to observability. And like in a musical score, there's the part that you play. That's the transaction. That's a request. That's where you want to have tracing, right? That's where you want to do debugging. What was this node here? And what was this variable in the stack here? And this, stack trace there. That's your transaction that it goes into the systems, goes deep and comes back out, right? That's the kind of visibility that the developer needs because I'm coding my happy path, right? I want to see like, how does it actually work in production? And if it doesn't, what happened? Why did it not happen? What was the assumption that led to this bug? That's the bug thinking, right? But then there's the entirely in the y-axis. That's the axis of the conductor. How do all these parts work together, right? And the larger it becomes, like in a large orchestra, the more important this aspect becomes. Right? So that's what we are dealing with. We are looking at the y-axis of observability, not the x-axis. The x-axis, we have tons of tools, right? Mostly really interesting at the local level, right? For the single part, right? So the operational concerns, how does everything work together? Right? So just to make sure that's really, really clear, another analogy. Do we need the pilots or do we need air traffic control? Right? If I'm in charge of a single flight, yes, I want to have super deep observability and tracing. What's the oil pressure on engine 2? Right? That kind of stuff. But if I have thousands of planes that are all decoupled, 2 pizza teams flying in the sky, I need to manage that. Everything is unpredictable. I can have as many flight plans as I want. I need to manage the unpredictability, right? So that everybody can operate independently, right? Because that's what the business needs. The business needs to be able to run in an agile manner, right? That means everybody needs to decouple. I need to have my 20 or 200 development teams or 2,000 development teams deploy in parallel without having to wait on somebody else, right? Like each plane needs to be able to fly independently. That's what we do, right? We manage that unpredictability. And the key ingredient here, of course, is very high visibility, high level visibility, and then real-time control, right? So those are the ingredients. High level observability based on real-time signals. We call them golden signals. For an air traffic controller, obviously, that is position, altitude, direction, speed, maybe a little bit of weather data thrown in. For us, it's call sign. Oh, I forgot the call sign, of course. It's the service name. It's how many requests are running. What's the latency on those requests? How many run in parallel? How many threads? How many workers do I tie up? Connection pool issues, right? These kind of things. And then bandwidth. But crucially, we need those golden signals for everything that's in our airspace. If there's anything in there that we don't know about, we can't manage, right? So entirely different orientation. Instead of going deep and providing like insane levels of details about a single execution, we go broad but need to have signals about everything, right? So this is how it looks like then. If you have these kind of signals, you can assemble a service map, like here, the Google traffic map on the left side, where, like in downtown San Francisco, these things are always red. So something I may want to look at. On the right side, you keep track of things you've already looked at, right? So you get a sense of what's happening at a very high level, at the forest level, not the tree level, right? And then armed with that kind of observability, you can immediately do something about it, right? Doing something involves things like, in the Robinhood case, my DNS services get clobbered. Why not exert like what every operator has done in the past 50 years? Classic back pressure. Well, okay, because I didn't have the ability to do that, right? At Robinhood, yeah, a little bit negligent. You need to have the ability to do something about it, right? You have unpredictable architectures. You need to be able to do something, right? So same thing, bulkheads to zones to regions in your architecture. They shouldn't be talking to each other, past beyond a certain point level. Absolutely, another capability. Quarantining new deployments. Something rolls down a CI/CD pipeline, absolutely ring fence it, quarantine it, right? Your Hadoop cluster is a little bit slower. Why not load shed a little bit? Right? That allows you to really shape the digital experience across your entire service landscape, your entire digital landscape. Right? This is just an example service pattern catalog. Think of these as best practice, really highly predictable and effective operational patterns. That if you look at books like Release It, right? They talk about these things all the time, right? So segmentation from a security perspective and so forth. And many other patterns like this. This is just a sample catalog. How does this look like once it is really done in production? This is a sample, a bulkhead expressed on 3 dimensions. There's requests, there's concurrency and bandwidth. So in this case, between analytics workloads that are near real time, but not real time. And the real time system, as an architect, I want to have a bulkhead in there to get some predictability. These teams work independent of each other. That gives me predictability. And that's something I'm going to have in the architecture, most likely for an extended period of time. You see, it just clips in each dimension. It clips the spikes, the microbursts. That's it. Otherwise, it doesn't slow anything down. But it buys you a lot of predictability, as an example. That's how control looks like. Another example, just generation, something that happened as was published at an American supermarket chain. I'm just going to give you the high level of that, so you get a sense of like what these operators are dealing with. Imagine you're operating this bunch of services, VMs, Kubernetes clusters, all kinds of stuff. You come back and you see like alerts like this, right? Bunch of red things, right? Things are slow, stuff doesn't return, these kind of things. Now you go on a Safari, right? like any engineer would do. You would discover, oh yeah, my Kubernetes cluster here is, it seems to be crashing, moving pods around like crazy, right? What's wrong with these pods? Then you realize, oh, nothing's wrong with these pods. Eventually all pods are being moved. So why is that happening? And hey, why is it only this cluster and not other clusters, right? You try to get closer to the reason of that, right? Then at some point you realize, oh, it's this cluster maybe because it has large nodes, right? It's a large cluster with many nodes, right? And then you look closer and you realize, oh, we get huge CPU spikes in there. And that squeezes the Docker daemon. And then Kubernetes does what it's supposed to do. It kills nodes, right? Back to Laura Nolan's talk, like one of these things, automations that clash, prime reason for failures, right? There's something programmed in there that kills your system because it does what it's supposed to do. So we are in an automation-rich environment these days, right? So now what do? Why is this happening? Why do you get like large, high CPU spikes? Turns out, well, all my sidecars are thundering here. So for some reason, the sidecars that I've injected because it was smart and said, hey, we all want to log to the same destinations and all that, and we want to do this in a uniform way, all kind of like doing this at the same time. So what's happening here, right? They haven't done this before, right? Then you realize, oh, the Kafkas that they're actually logging to are hiccuping. They're there sometimes they're not there. So when they're back, everybody wants to log, and that kills your Kubernetes, right? And then you inquire further, you find out, meanwhile, it's past lunch, it's in the afternoon. Oh, somebody did an OpenStack Neutron upgrade, right? And like it always is, oh yeah, it's only going to be like 10 seconds, right? Let me reboot this machine. And that led to a whole day of like flip-flopping on the Kafka side, on the OpenStack side, right? But the morale of the story is really that you wasted your whole day going down rabbit holes, one after another, an endless story of rabbit holes, only to discover that the solution is entirely outside of your control. It's out of your control, right? It's in a totally different side of the house. You have nothing to do with OpenStack, right? So here's how it would play out. If you had runtime control, you would see on the left side immediately, everything is red, tons of traffic here. All these sidecars here hitting these purple Kafka, as an older screenshot, but hitting those Kafka endpoints. And on the right side, you see dropouts, choppiness, huge spikes of demand and stuff like that. All the stuff you really don't want to see. Now, the important thing here is you don't care what the root cause is. You do something about it right there. You're like the emergency medical team that there's somebody on the side of the road. You look at the pulse, you look at the temperature, you look at the pupils, and here's the injection. Stabilize the patient right there within 10 seconds. Right. So what do? Very simple, classic back pressure. You say, hey, guys, 10 at a time, 1,000 at a time, whatever the number is, bring order into the chaos, calm things down, right? And that causes nothing to thrash anymore, right? Because everything is, you bring order to the chaos. Right? So the situation is under control within a minute, and without even thinking about a root cause, simply because classic back pressure, maybe a little bit of circuit breaking of long running requests that don't have any chance of returning anyways, right? So that's the power of runtime control, right? That's why we focus on super high level visibility and immediate runtime control. Right? So now, of course, each organization is different. And you may say like, well, we have a different architecture and we work differently. Our culture is different and so forth. Totally correct. But keep in mind, there are stages of acceptance for cloud chaos, right? And I think there are 4 stages, and there's things you can do as practitioners, as developers, or as operators in each of these stages that I want to walk you through. And of course, stage 1 is denial. That's the VP of engineering that you may have, or maybe know of, who says, yeah, yes, it's a little bit chaotic, but frankly, I'm going to get my guys to not write bugs anymore, right? We've all seen these guys. They show up at the company and 6 months later, they're gone. The company is in a worse spot. Of course, that doesn't help at all. There is no such thing as like not writing, writing code in a way that you can avoid, unpredictable events. So this at best becomes micromanagement. But what it can do in that time, and as a result of this micromanagement, obviously, innovation dies. There's nothing you can do. It's just everything slows down, right? You can build in compensation strategies on the development side, right? To handle failures. There's some things that you can prevent very locally, make local decisions. It's a small set of things, but you should do that, absolutely. Something doesn't come back in a certain time. For your functionality, you can make the decision whether you want to move on, for instance, right? Also, shift left, absolutely invest in heavy unit testing, right? It's super high value and cheap to do this on the left end of the DevOps spectrum. It becomes really expensive and low value on the right side, the further you go right. Second stage is the more advanced companies that says, yes, there is chaos. We're going to fight it. We're going to bargain with it, right? And you know what we're going to do? We're going to re-platform and we introduce strict standards, right? And that works for a certain amount of time, but it's golden masters thinking. It's like we did with VM images back in the day, right? You release the golden master, great idea, because everybody builds on that golden master. The moment I release it, some other package gets upgraded, the master is updated. So nobody ever uses golden masters. And this is what's happening to these re-platforming efforts at a massive scale and at a immensely costly scale. But still, as a developer, you can do something at that stage. You can make sure you absolutely, like the devil, avoid distributed systems engineering. If you need primitives that have true distributed systems characteristics, they're already done, right? Use a Paxos and use Erlang in a core piece or something like that, right? Use a Cassandra, right? These things are solved, right? My favorite thing here is always remember, in nature, there is no such thing as a distributed system. It doesn't exist. Everything is parallel in nature, right? It's a fiction. It's a figment of the human mind, because we want to extend a very simple mental model into a more complex environment, right? I want this transaction to execute in parallel across 100 machines, right? It's difficult to do, yeah? So avoid this like the plague. It's an anti-pattern. Default to eventual consistency. That's a lot of things we can do as developers there, right? Also, resort to redundancy and plausibility checks, right? If X9s of accuracy or something is important to you in a certain use case, do things several times where it's required, where it's really valuable, right? Otherwise, just eventual consistency is totally good enough. And then, of course, build resilient foundations, like small, highly domain-driven base services with as much built-in resilience as possible. So you can hammer on them. They don't fall over. They're robust, right? Third stage is nothing has happened. Nothing has helped. My replatforming effort was a complete disaster. Ops goes into depression mode, right? It's like the chaos is real. There's nothing. It's always greater than what we can do. All we can do at this point is slam the brakes. No, we can't deploy this. This is when you talk to the executive and the VP says, or the CIO says, yes, it was horrible before cloud came, but then the cloud came and everything was great. And now it's worse than it was before because of complexity. So that's just stasis. Nothing works anymore. You're in a dying company and so forth. There's one thing we can do at that stage, and that's simply accept that if we stitch things together, which we want to do because the business needs to move fast, we need to accept the chaos. There is cloud chaos, and defer as much as you can do to runtime control. Now, that gets you to stage 4, which is acceptance, where you look at how can I control this chaos in runtime? And there's a bunch of things that we need to do as operators. Number 1 is realize that code doesn't matter. It simply doesn't matter anymore. Anybody can write code, languages, it gets simpler, frameworks are there, we use other code that's there and so forth, right? It's very easy to whip up functionality these days. It's not like writing a C program in the 80s, right? With a $10,000 compiler, right? What matters is the environment. Realize that the environment is really the only thing that matters. Focus on unexpected environmental factors. Is there any noisy neighbors? How would I pick up on that? Right? Invest in these capabilities. Right? Then invest in rapid detect and response cycles, MTDR, mean time to repair, right? Loops. So you can control the unpredictable. By the nature of things, unpredictability is unexpected. You can't prepare for it. Right? So you need to be able to very quickly observe and act, right? Detect and respond to these events. Right? And that means ultimately monitor for golden signals. Whatever your set of signals is that you believe is the right one, monitor it and then apply effective operational patterns to control that in real time. Right? Do not ever fall for root causes. There is no such thing. In these architectures, there's no such thing. Right? There's always, it's like a dysfunctional family. There's no single person is at fault, right? It's a confluence of things, right? If you think, oh, I'm going to do a root cause analysis, you're lying to yourself and your business and your team, right? It just doesn't exist, right? It's intellectual laziness. It's nice for us to think that there's something like a root cause. It just practically it doesn't exist, right? And they're highly expensive to chase. It takes you a whole day to get a result, and then you have never explored an alternative, right? So it's a fantasy, right? Then fight the urge to debug anything in production. Don't try to like, oh, Wireshark this and Wireshark that, right? Or it's a waste of time. Leave tracing to the debuggers, to the developers. Once you have the situation under control, right? As an EMT on the road, your job is to stabilize things. And if there is something the doctor in the hospital wants to look at later, by all means, let the doctor look at this later, but not while the patient is on the street, right? And it's not your job. It's the developer's job who knows the code, right? And finally, realize that in these kind of architectures, architecture is a management function. It's a runtime. Architecture and operations become, more or less one. You're moving capacities around, you change designs at runtime, you influence interactions, you influence flow, and that's a runtime function because things are unpredictable. Right? So that's the takeaways really of the talk. And a bunch of things we can do on the developer side and a bunch of things we absolutely have to do on the operations side. And that applies to all decentralized architectures, not just microservices. If you have mainframes, from mainframes to serverless, anything that's an endpoint in the network. So I would say at this point, I think, Dave, correct me, we said 445. I have more slides. I can go on, but interrupt me.
I think you're doing quite well. If you want to go a couple more slides, I think you're fine. I think what I'd like to do is ask the attendee. We've had a few people join, by the way. So for those of you who joined, if you have any questions, you're more than welcome to ask them in the chat, or you can actually ask them by unmuting yourself. So, if you feel that that's a good option for you, feel free to do so. We're keeping this sort of low key and casual.
Yeah.
But if you're making great times. If you want to go a few more slides, go ahead, and maybe I'll ask you some questions. Actually, I have one question for you, which is there a type of application or style or that you see requiring this kind of management the most? I mean, you mentioned
Yes.
some like, mainframe and, all these different types, but is there one that's kind of standing out or which is kind of growing the fastest?
Yeah. So the most important, first of anything we do applies to digital landscapes, to service landscapes, right? Modern environment where things are loosely stitched together, where multiple teams deploy into a service fabric, if you will, right? Where there isn't really an overarching blueprint of things. Right? We see these environments becoming pretty much commonplace in enterprises now. It's not the 10-person San Francisco startup, right? If I'm a startup, I have one product, I have exactly one application. I'm going to build the application exactly how I built applications 50 years ago, just with a different tech stack. What is different here is that there is no application anymore, right? We have a set of services that may form islands that resemble an application, a core set of services here, another set of services there, but they're highly connected. Everything has an API, right? So that makes interactions, very unpredictable. I am suffering from noisy neighbors. There are feedback loops. There's compounding slowness. There's cascading failures. There are the random ripple effects. Things are nonlinear, up the wazoo. It's really difficult to make sense of these things. But at the same time, we do want to run these architectures, right? Because the business needs speed, needs fast time to market. And the only way we have an agile business is by deploying just willy-nilly, stitching things together. So that's, if you're in that mode, that's when you need runtime control, right? If you're pre that mode and you think you're still doing okay with a single application, microservices or not, right? You have like 20 services that are otherwise standalone, self-contained. It's a single blueprint, single Git repo, right? You probably get away with normal engineering. You discover something, you monitor, you discover, oh, this is kind of not working right. You write a ticket, the developers go in there, change code, run the entire pipeline again, deploy it, hope that it works, right? That's a really old deployment model, right? You cannot afford that if you have 50, 100, 200, 2,000 services or more, right? Because I don't know what code I should change here to get this, this feedback loop resolved, right? And by the way, if I think, oh, it's this feedback loop over there between these services, right? Circular dependencies, so these kind of things. Let's put in a circuit breaker. That circuit breaker now becomes next week the reason for the next outage, because everybody forgets about it, right? Oh, let's put this code in here, right? And so we need to get out of the habit to define interaction behaviors in code. That is a runtime activity. Again, it's like air traffic control. Or if you prefer, if you are a manager in an organization, the business gives you a new strategic initiative. You reorganize your teams to implement that strategic initiative. You're not going to lean back and now let them work. That doesn't work. It requires daily, constant management. That's what management is all about. Make sure these things work together, the y-axis of operations, right? But for historic reasons, we don't do that in a large scale in the IT world yet, right? So that's the capability that we bring to large environments. Does it make sense?
You see those Death Star diagrams with all the services connecting to each other, and sort of as soon as you get to one of those where you can't see all the individual dots, you're probably needing something like this.
Absolutely, right? The Death Star starts pretty early. 100 services, 80 services, absolutely there, right?
Right. Okay. And we got another question here for you from Mahesh. Mahesh, I think I've unmuted you, or you can unmute yourself now and ask your question.
Yeah, absolutely. Thanks, Dave. Absolutely super great talk there, Tobias. Really enjoying it. And my question was along the lines of what Dave queued up earlier on. Just curious, you mentioned air traffic control. This looks like large fleet management, fleet remediation, and automation of that remediation. I was wondering if you can share with this meetup group maybe a practical example of of issues that you detected that were inching, sort of taking that patient analogy, inching towards a stasis situation, and how Glasnostic was able to thread together those, golden metrics, if you will, those signals, and then, create a remediation path.
Yeah, one example was the supermarket example that I tried to narrate, right? Which we didn't do, but it's a very specific, very like typical example. Think back to Robin Hood, right? If Robin Hood had used Glasnostic in their infrastructure, the outage would have lasted 30 seconds, right? Because it takes very little time to see the red lines, to see that something extraordinary is going on there. And then it takes you another 10 seconds to do something about it. And the key here is, the value here is really in real-time control. The value is that I don't need to worry about root causes. I'm remediating. Remediating by definition means it's not a diagnostic, right? It's not 10 hours of like searching for something. It's giving the patient that shot, putting the patient on a gurney, right? Putting this cast on. That's what we do. And that is where the value is. So if I flip forward, if you just compare what you can do without real-time control and what you can do with real-time control, right? You get to see what's happening, right? But for the more development-oriented operations teams like the DevOps, the SRE, and SecOps teams, right? If I can't do anything in production, I need to expensively stage things in pre-production somewhere. And then I need to very awkwardly define interaction behaviors somehow in code. That's when you see stuff in YAML that says num retries 3, right? Of course, as it evolves, these 3 retries is the cause for the next outage a couple of days later or months later, right? Because you need to define things in places where it doesn't belong, right? The code doesn't know who's going to call that shared service a month from now or a day from now, right? With runtime control, you can adapt to that in real time. You can adapt to these changes, right? Any unexpected things you can remediate in real time. Whereas otherwise, things just blow up and then it takes you a day. And yes, the business takes the hit, right? For the more service delivery oriented operations guys and larger organizations, right? Service delivery, these teams, they have tons of tools already, but none of these tools are really connected to actions. With us, because we can take runtime control, you can connect them to a central control plane, right? You have a vulnerability scanner running somewhere. It discovers, oh, there's a zero-day patch, a zero-day vulnerability that hasn't been patched. Connect it to the control plane, take this guy out. Right? Doesn't even need to file a ticket. And overall, you can just shape how your entire service fabric, your digital landscape works for the digital experience. Right? So everything hinges around this capability of being able to do something in runtime, which we can in all other areas except for IT. Right? Air traffic control does it. Management does it. Heck, as it said earlier to somebody else, like, the kindergarten teacher does it, right? You wouldn't go out of a kindergarten classroom and say, hey, kids, do something for 5 minutes. I'm going to go somewhere. This stuff is going to blow up in 4 seconds, flat, screaming, right? Chaos going on. But that's how we deploy things, right? It's just abstract capacity. So we bring the kindergarten teacher back that moderates how everybody talks to each other.
Okay, great. Let's see. I think that's it for the questions so far. So if you have anything you want to wrap up with, I think this would be a good time.
Yeah, there's one thing that I think is always a good quote to end, a note to end on. John Allspaw, who was the CTO at Etsy, now runs his own consultancy, right? Wrote a whole master's thesis on incident management and the human factors in that. And the last paragraph, I cut it down a little bit, but essentially it says is that, hey, everybody, we always think that if we're like the prowess of, of software systems, averts outages and failures, and it's actually not true, right? Because we live in highly automation-rich environments, and the adaptive capacities of human cognition and activity read control, right? That's really what makes the difference, and not the pseudo intelligence of software. Yeah. Last paragraph in the master's thesis, I think one of the best paragraphs written on the topic.
Yeah, excellent. Thanks for sharing. Great. All right. Well, I think with that, we're getting close to the hour, and I do want to just wrap things up in a minute. So I want to thank you very much. I think we're all going to give you a sort of virtual applause here. And thank you very much.
Hold on. If you want the sticker, this is how it looks like. Here.
I like it.
Get a grip, laptop sticker. Let me know or let Dave know, and I'm going to send it out.
Yeah, you can let either of us know, because I'll be sending some out too as well. So if we want to just combine efforts, we can do it that way.
Or just send it to Dave. Yeah.
Yeah.
Easier.
Great. All right. Thanks again. And also congratulations. I heard you guys had a announcement. You are now offering your service with on AWS. You want to just tell us a little promotion for yourself here, what that's all about?
Yeah, super exciting. We were a launch partner 2 days ago with their new Gateway Load Balancer service, which is the first in a series of like networking related, interaction related services that are going to come out, where we simply just plug in. So it's a one-click install. Those shaping runtime, real-time control capabilities is a one-click install to any VPC-based architecture now, right? So super exciting. We were launch partner alongside with the likes of Cisco, ACI, Fortinet, Palo Alto Networks, these kind of places, right? So really exciting that we as a small company got to do that. And there are more to come.
Yeah, that's really cool. Nice. Yeah. Well, congrats. Yeah. Congrats on that. Integrated with the largest cloud is a pretty good step. So, okay. Well, thank you again. What we're going to do now is we're just going to wrap things up. We still got about 10 or so folks still on here, and I want to make sure that everyone gets a chance. We're going to have a raffle for $50, just like we did last week. And I'm going to do the raffle simply. I've got a web page here. It just is a little random number generator. There's 10 of us. Let me click 10 max. I'll hit generate. Oh, and how random. It chose 10. Who is the last one here? Let me check. And the last one is Sean Murphy. Sean Murphy, you get $50 gift certificate to your choice. And everyone also gets a t-shirt and a sticker if you'd like it. So I'll just send out an email to all of you. I also was asked about your slides. Is that something that you can make available?
Oh, absolutely. Yeah. Yeah.
So I'll make your slides available in the email, and make sure that you all get a chance to ask for a sticker and a t-shirt.
Absolutely.
So with that, Sean, I'll reach out to you and get you your gift certificate, and we're all set. I just want to let you know, we also have a couple talks coming up. We have next month, we have Charity Majors from Honeycomb who will be speaking. And we also have ongoing series. So Mahesh and I are organizing some other speakers, and we'll do this every month on this specific topic, and that is independent of any Silicon Valley DevOps meetup talks we have. So some months we might have 2 talks. So we look forward to having you back again. And with that, we'll wrap things up. Thank you again, Tobias. Thank you everyone for joining us, and look for an email from me with follow-up. We'll talk to you then. Okay.
Thanks for having me.
You bet.
Thanks, guys. Thanks, everybody.
Bye, everyone.
Thank you. Bye.
Bye.